You know, we think we understand electricity, right? It's the light switch on the wall, the charge in our phones. But what if I told you that every single electric current has a secret life, a hidden personality that's completely invisible but unbelievably powerful? Let's pull back the curtain and meet electricity's magnetic alter ego.
It all really boils down to this one simple question. You've got a regular old wire with some electricity flowing through it, and you've got a compass, which just wants to point north. You'd think they have nothing to do with each other, right? But bring them close, and something really weird starts to happen. So what's the secret connection? That's the mystery we're going to solve together.
And our story doesn't start in some high-tech, fancy lab. Nope. It kicks off in the middle of a totally normal lecture with a complete accident that, believe it or not, would end up changing everything.
Okay, picture this. It's 1820. A scientist, Hans Christian Oersted, is up in front of a class, showing how an electric current can heat up a wire. He flips the switch, the current flows, and all of a sudden, a compass sitting nearby just twitches. Its needle jumps, totally ignoring the North Pole for a split second. Now, this was a tiny little thing, a fluke he could have just brushed off, but he didn't. And in that one moment, Oersted saw the very first clue that electricity and magnetism weren't strangers. They were family.
Now, to really get what Oersted stumbled upon, we first have to understand the world his compass lives in. It's a world run by a totally invisible force, and to find our way around, well, we're going to need a map.
This is so cool because it literally makes the invisible visible. If you just sprinkle some iron filings around a bar magnet, they don't just fall wherever. Nope, they snap into this perfect, beautiful pattern. And these lines you see, they aren't just for show. They're a literal map of the magnet's power, its magnetic field.
And like any good map, there are rules. Think of these lines like tiny one-way highways. They always flow out of the North Pole and loop all the way back around into the South Pole. And you see where the lines are all bunched up together? That's where the magnetic force is the strongest. And here's the most important rule of all. These lines, these paths, they can never, ever cross each other.
So, we've got the rules for regular magnets. Now let's jump back to Oersted and his wire. It turns out that current flowing through the wire was secretly creating its own magnetic field, with its own special map.
And there's a kind of secret handshake to figure it out. It's called the right-hand thumb rule. Seriously, try this with me. Pretend you're holding a wire in your right hand. Now point your thumb in the same direction the current is flowing. See how your fingers naturally curl around the wire? That curl, that's the exact direction of the magnetic field. It's so simple, but it's incredibly powerful.
Okay, now what if we take that wire, and instead of keeping it straight, we coil it up into a tight spring with lots and lots of loops? Well, we've just created something called a solenoid. See, every single one of those loops creates its own little magnetic field. By stacking them all together like this, we're concentrating all their power into one super strong uniform field right down the middle.
And check this out. On the left, that's the magnetic field from our solenoid. On the right, that's the field from a normal bar magnet. Look at them. They're almost identical. A simple coil of wire with electricity running through it is acting exactly like a permanent magnet. But here's the real kicker. This magnet, you can turn it on and off with a switch.
Okay, let's recap. We know magnets have magnetic fields, and we now know that electric currents create their own magnetic fields. So, the big question is, what happens when these two invisible forces actually meet?
It's not peaceful. The two fields interact, they push and pull on each other, and bam! A real physical force is created. The wire is actually pushed, it moves. This right here is the climax of our story. It's the moment an invisible electrical property creates real, visible motion. And this is the fundamental secret behind every single electric motor in the world.
And you guessed it, we have another handy trick to figure this all out. This time, use your left hand. Point your first finger, your forefinger, in the direction of the magnetic field. Then point your middle finger in the direction of the current. Now stick your thumb straight out. Whichever way your thumb is pointing, that's the direction of the force. That's the way the wire is going to move.
All right, you've seen the accidental discovery, you've learned the secret handshakes, and you've seen the two forces collide. Now it's time for the final challenge. Let's put all this new knowledge to the test.
Okay, first question. This one goes right back to our magnetic map. We said the lines can never ever cross, but why not? What's the big deal? The answer is actually really logical and kind of beautiful. Remember, a magnetic field line just shows you which way a compass needle would point. So if two lines crossed, it would mean that at that one single spot in the universe, a compass would have to point in two different directions at the exact same time. And, well, that's just impossible.
Okay, on to challenge number 2. Get that right hand ready again. Imagine you have a loop of wire lying flat on a table in front of you. The electricity is flowing around it clockwise. The question is, inside that loop, is the magnetic field pointing up, away from the table, or down, into the table?
Let's use our rule. Point your thumb so it follows the wire in that clockwise direction. Now, look at your fingers inside the loop. Which way are they curling? They're curling down, right? That's it. That's your answer. The magnetic field is pointing straight down, into the table.
All right, this is the final boss, the big one. Now remember, a moving positive charge is basically just an electric current. So imagine this little particle is flying west. Out of nowhere, an invisible magnetic field pushes on it and it gets deflected north. So, using your left hand, can you figure out which way that magnetic field was pointing?
Let's break it down with Fleming's left-hand rule. Okay, your thumb is the force, so point it north. That's the direction of the deflection. Your middle finger is the current, so point it west. Now, just look at your forefinger. It's pointing straight up. The magnetic field had to be pointing upward. Fantastic job!
So you see, Oersted's little accident and these simple hand rules, they aren't just fun party tricks. They're the literal keys that unlocked our entire modern world. That tiny push on a wire, that's what spins every single electric motor. It's what makes the cones in your loudspeakers vibrate to create sound, and it's how microphones work in reverse. This relationship is even at the heart of medical tools like MRIs, which use incredibly powerful magnetic fields to see inside the human body.
So, the crucial thing to take away is this. That tiny, accidental twitch of a compass wasn't just a neat little discovery. It was a revolution. It proved that electricity and magnetism aren't two separate things. They're two sides of the same coin, a single unified force called electromagnetism. And it's a force we've harnessed to build pretty much everything that defines our lives today.
It really makes you wonder, doesn't it? From one person just noticing something a little strange, a whole new branch of science was born. What other incredible forces and secret connections are out there hiding in plain sight, just waiting for the next curious person to stop and say, "Huh, that's weird."